This video is the first lesson for Physics 12 for Chapter 6 for electric circuits. And you probably want to write some notes and copy along, but right off the start, actually, I'm going to invite you to put your pencil down and just look at some stuff for a minute, and then we'll definitely jot some stuff down in a couple of minutes. But yeah, pencils down for just a second. Just watch, if you would, for just a minute. Just going to kind of go over some of the stuff that we saw in Physics 11 about just the difference between conductors and insulators. I should tell you that some of what I'm showing you here is fairly metaphorical and not exactly the way the physics works, but it can just help you kind of get the right mindset for what's going on. So for insulators, these are materials such as glass, where electricity cannot easily flow through the material. And the example I've got here is actually just some helium gas. So I've drawn a couple of helium atoms with their 2 protons and their 2 orbiting electrons. And I've got a little metaphorical brick wall there saying that, yeah, it's not really energetically favorable for an electron from one helium atom to migrate over and park itself in orbit around another helium atom. So there's no easy way for those electrons to jump from atom to atom. The atoms are tightly holding on to their 2 electrons, and there's no easily room for more without going to a different orbit, and they just tend to hang on to them pretty tightly. But if you go just one element up in the periodic table, and again, you don't need to copy this, this is just to look at. If you take a look at lithium, lithium is atomic number 3. It's got 3 electrons, and 2 of them are tightly held. It's not going to give those up, but the last one is actually fairly loosely held. And that orbit out there has actually got a lot of room for more electrons to kind of migrate in and out. So you have this conduction electron that's weakly held, easily removed, and then spaced for more should any other electrons want to arrive. And so what I've done, again, this is a bit metaphorical, but you kind of get the idea. I've shown you what it might look like for a little chunk of lithium metal with the atoms fairly close together. They're actually close enough that their orbits, in an energy sense, start to overlap. And the electrons from one can actually pretty easily migrate around and then just move over to the orbit for another one. So this could happen. So I've had the electron from the atom that's now shown in pink go and jump over here. So this atom's got 4 electrons. This one's only got 2. Again, from a purist physics point of view, this isn't exactly right, but it's kind of the right idea anyways in terms of how the electricity is going to work. The atom that's had the electron leave is now positive because it has its 3 protons and only 2 electrons. And the one that's had an electron arrive is now negative. Overall, the chunk of metal is still neutral, but this electron is now hopped from one to the other. Quantum mechanics would say that you can't really localize which atoms got the extra electron, but yeah, for now, just for some quick little pictures, it's fine. So we've got this ability to have electrons move around in conductors from atom to atom. If you take a big chunk of lithium and you want to charge it negatively, maybe you're doing some electrostatics experiment, you could sprinkle a few extra electrons on there and it might look something like this. Again, formally you wouldn't really know which electron, or I should say which atom has the electrons on them, but some of those atoms have an extra electron in there floating around in that outer orbit. And those outer orbits are overlapping in an energy sense, and those electrons can just kind of bounce around from one atom to another. If I zoom out a little bit, it might look like this, right? Just getting a little farther and farther out. At some point, the resolution on YouTube here is probably not even going to let you see this, but if I keep zooming out, then these atoms occasionally have an extra electron on, and they can move around, right? Those extra electrons can hop from atom to atom. It gets visually pretty distracting drawing all those little atoms, so at some point we say, look, don't even bother drawing the light blue stuff. It's all neutral anyways. Why don't we just highlight that there are some places that have an extra electron? And so we just draw this, right? So all your little textbooks say, oh yeah, I charged up this piece of metal negatively, and they show all these little negative dashes, and that's just where you've got a few extra electrons. So that's how you make a material negative, is you add a few electrons to it. If you want to make a material positive, you don't do that by adding positives. Instead, you go up to a couple of those atoms and you extract some of their, well, an electron from some of those atoms. If it was lithium, you'd just be extracting 1. And so you might have a couple of lithium atoms like this that are missing their electrons. So now they're actually positively charged. They have their 3 protons, but only 2 electrons. And zooming out, again, might look like this. And just like with the last story, it gets a little visually distracting once you zoom out far enough. So at some point we say, you know, the light blue stuff's not all that interesting. Those are just atoms that are balanced. But there are some atoms that are missing an electron, so they're positively charged. Why don't we just highlight that there are some positives? But when you draw it like this, which is the way we usually draw it, kind of gives you the impression that you're adding positive charge. But you actually accomplish that by removing some negatives, right? It's the electrons that are mobile. But it's just easy to draw that by showing some plus signs. Okay, electric circuits, that's what this chapter is all about. What happens if you take a wire, maybe made out of copper or aluminum or even lithium, and you connect it up from one terminal of a battery to another? Well, then you're going to get electricity flowing through that wire because the electrons can essentially hop from atom to atom to atom. So let's zoom in on maybe a 9-volt battery here on the terminals. And again, this is a bit metaphorical, but we can go with it. On the negative terminal, which is the larger one on a 9-volt battery, I've shown some atoms there that have extra electrons on them. And the positive terminal, I've shown some atoms that have had some electrons removed. The wire is going to now conduct that electricity by allowing some electrons to hop along. It's kind of neat the way the chemistry can actually pump, it can move the electrons from the positive terminal to the negative. They don't really want to leave the positive terminal, and they certainly don't want to all pile up on the negative one, but the chemistry can actually force that to happen with a couple of what the chemists call half reactions. Okay, so here's the wire. I'll just draw it as lithium again. What could happen, again, it doesn't go exactly like this, but it's close, is you could have an electron leave that negative terminal and say, hey, I want to get out of here. I'm repelled by all these other negative charges, and I'm going to go and just hop my way along from one atom to another, because it can do that, right? It can freely move along that kind of outer orbit, jump from one atom to another, and make its way over to the positive terminal, where when it jumps and lands on the positive terminal, kind of neutralizes one of those atoms, and then the chemistry goes, oh, let's grab that, push it back over here, and it does it again. Now, it doesn't do it one at a time. To be fair, there's kind of this multitude of hops that are happening continuously, kind of like pushing marbles through a pipe. But it's essentially the electrons that are hopping along from the negative terminal to the positive. So this is how the electricity actually flows. You're actually moving charge, but it's negative charge from the negative terminal to the positives. Now, Benjamin Franklin, when he was first playing around with electricity, he had to make a judgment call. Which way is the charge actually moving? Is it positive charge going from positive to negative, or is it negative going from negative to positive? Made a judgment call, got it wrong. It's our one big mistake in physics. We still honor that mistake to this day. We draw all of our pictures for electric current going from positive to negative, knowing full well that what's really happening is electrons are being in this little jumping arrangement from the negative terminal to the positive. But we don't fix this now. We're just going to say, yeah, whatever, and we'll just talk about it as being electric current. So whenever we talk about current, it's always as if it's a positive thing going from the positive terminal to the negative, even though we know it goes the other way around. Okay, let's just write a couple little notes down after you've seen those pictures. I would write this down. So a quick little review of grade 11. Only these negatively charged electrons can move. Now, please don't get the impression I'm trying to say that there are positive electrons, although there kind of are. They're positrons. But what I probably should be saying there is only electrons, which of course are negative, can move. And not even all of them, right? Only the electrons that are on those conduction bands, on those outer ends of the atoms. The positive protons that are in that nucleus, they never move. They are stuck in that lattice that makes up the metal, and they're rigidly held. They can't move at all. If you've got a piece of metal and you want to charge it negatively, go ahead and add some electrons. If you want to charge a piece of metal positively, you can draw plus signs on it, but we actually accomplish that by removing electrons. Current is the next thing that we're going to talk about for electric circuits, and it's just a measure of the charge, how fast the charge is passing a point per second. The symbol for it is a capital I, and the equation, kind of in a formal sense, is actually Q divided by T. And you might think, oh, shouldn't it be V divided by R? That'll come later. That's actually next day's lesson. But in a just definition sense, current is all about how quickly you can move coulombs of charge over some time period measured in seconds. So it's actually Q divided by T. You can rearrange that, of course, and say, oh, okay, well, the charge that moves in total is actually just equal to I times T. The units for current are actually amps, and 1 amp is equivalent to 1 coulomb of charge every second that's actually moving. If you want to measure current, you have to make sure you protect the ammeter. You don't want to hurt it. You have to make sure that you first disconnect the circuit where you want to measure the current. You create a break, and then you insert that ammeter in series. Whenever we draw meters in physics for electricity, they're always named with little letters that indicate the units. So we don't actually put in an I in the label for a meter for current. We actually call it an ammeter because it's measuring the amps. It's just easier to drop the P. And we put an A in there. Okay, so let's say you had a circuit like this. Hold off on drawing it for 2 seconds. Okay, so I've got my battery with the bigger line being positive and a little resistor to slow it down. And I might want to know, hey, how fast is the electricity flowing through there? So what I would do is create that break like that. I would disconnect the wire, and then into that break, that's where I would connect the ammeter. The ammeter is designed to have very little resistance. That way it'll let the exact same amount of electricity flow, but it just monitors it and lets you know how many coulombs per second are flowing by. The current, again, we're just going to talk about it as being something that comes out of the positive end, the larger line on the battery, going towards the negative end. Yes, okay, it's our one big mistake in physics. Actually, electrons go the other way. But whenever we talk about current, we're just going to draw it in as going from positive to negative. Please don't connect the ammeter like this. That will instantly damage the ammeter. They have very, very little resistance. And so now there's this path that lets the electricity go around that circuit without being slowed down by that big resistor. And so that would create massive amounts of current, which usually instantly damages your ammeter. So make sure you don't connect things in parallel for ammeters. Make sure they're connected in series. And really what that ammeter is doing is it's just telling you how many coulombs per second are passing by that one spot. And we just measure that in what we call amps. All right, let's just do a quick little example here. If 2.5 amps are flowing through a wire, how many electrons pass in 34 seconds? Well, I know that I is just equal to Q over T, and I can rearrange that and just say, okay, Q is equal to IT. And I can take my 2.5 amps, 2.5 coulombs per second, and multiply by 34 seconds, and then I can get my 85 coulombs. So I don't normally put units in on the fly, as you know, but I guess here it would be like coulombs per second, and then we've got our 34 seconds, and then the seconds, of course, cancel, and we get the 85 coulombs. That does not answer the question, though. The question was how many electrons go by in 34 seconds? More than 85. An electron is nowhere near a coulomb. But now that we've done the electrostatics chapter, we can say, okay, the number, and I just picked a letter of the alphabet, like N for number. The number of electrons is our 85 coulombs divided by the amount of charge on every single electron. Pretty tiny. So we end up with a whole bunch of electrons going by that one spot in 34 seconds. Now I'm just going to pause this video here for a second and see if I can fire up a little application here to let you see something. Just give me a second. Okay, so I've got a little simulation of a circuit going here. I think this one's got 2.5 amps actually flowing in it. And that resistor is kind of slowing everything down, which is quite nice. If I wanted to measure this current, I'd want to disconnect that circuit, create a little break in there, and then connect up that ammeter into that break in series. And so yeah, it's saying, yeah, you've got 2.5 amps that are flowing. One of the things that I wanted to point out, well, here's a couple of things. For starters, on an Energizer battery, that black end up there with the small terminal is the positive end, and we would say the current is actually going clockwise. You know, I know you look at it and go, wait a minute, looks like stuff's going counterclockwise. Yeah, those darn electrons are negative. It's our one big mistake. We would look at that and go, hey, look at that electricity beautifully going clockwise in that circuit from positive to negative. Another issue, when we figured out how many electrons, pass by in 34 seconds, if you watch these electrons, they're going to go around and around and around. So you may see that same electron going by many times in 34 seconds. And it's not a case of the battery running out of electrons, even though we say that in English. We say, oh yeah, my battery's run out of charge. I have to recharge it. But that's really not the case. The charge is already there. But what does happen is the chemistry reactions, there are a couple of them, that force those electrons from that positive terminal to the negative terminal. The chemistry runs out of reactants. And so to recharge a rechargeable battery, we actually drive the electricity the other way, and it turns all of the products of the chemistry back into reactants again. But we're not really running out of charge, even though we say, oh yeah, my battery has no charge left in it. It actually does. It just doesn't have the chemical reactants ready to push that electricity through. Okay, so yeah, with those 5.3 10 to the 20 electrons, a lot of them may have gone around many times. Battery capacity, this is new to Physics 12. We didn't talk about this in Physics 11. This is just a measure of the total amount of charge that's available in a battery. Again, here my language is already kind of a bit dangerous here, kind of giving the impression that the charge goes away and is gone. But this is how much charge is available to be pushed through the circuit before the chemistry runs out. It probably should be measured in amp seconds, but almost nobody does that. It doesn't quite sound right. So you could do amp hours, or maybe even, we'll see here, milliamp hours. It's some sort of story about current and time. So on a rechargeable battery, yeah, you'll probably see a voltage like every other battery, but you might see something like this, 2.3 amp hours. And that tells me that this battery can run at a level of 2.3 amps for 1 hour, and then the chemistry will be exhausted. You don't have to go at 2.3 amps though. You could go at less than that. So you could go at 1 amp. For 2.3 hours, as long as the product of current and time reach 2.3, you're fine. Now, instead of calling it 2.3 amp hours, you could actually measure in milliamps. Milliamps are smaller, so you end up with a bigger number, right? Instead of 2.3 amps, that's 2,300 milliamps. So this would be a pretty common way of describing the capacity, 2,300 milliamp hours. Yeah, and you can look at that and go, yeah, that's 2.3 amp hours. And there's nothing that says one of these numbers needs to be a 1. So you could also do 4.6 amps, but then the chemistry would be done after half an hour. As long as these two numbers multiply together to make, in this story, 2.3, that's when the chemistry will be exhausted. People sometimes ask you, hey, what's the total amount of charge in the battery? Kind of bad phrasing, really. They should say, what's the total amount of charge available to be circulated from this battery? But okay, we'll kind of talk about it as if it's the charge that's in the battery and it all falls out. So I could just take any one of those I's and T's. I might go 2.3 coulombs per second, 2.3 amps, and then go for 1 hour, 3,600 seconds. I want to make sure I'm working in seconds though if I do this. And I can see that the charge that's available is 8,280 coulombs. Again, it'll be recycled probably many, many times during that hour, but that's the point where the chemistry will be exhausted. Last thing we're going to look at in this lesson is voltage. Voltage, as you've seen in electrostatics, is almost a measurement of energy. Okay, it's the energy per charge. It's sometimes called electric potential, and it's the electric pressure that's going to push that electricity to go through that circuit. The symbol for it is a capital V, and again, we'll call it voltage or we'll call it potential, same thing. And interesting thing with the units here, 1 volt, 1 V, is going to be our unit. So we actually measure volts in volts. Unlike current, we measure current in amps or resistance in ohms, but we measure volts in volts. Or I guess you could say we're measuring potential in volts. 1 volt is equivalent to 1 joule for every 1 coulomb of charge. Okay, so I know we're going to write down volts and we're going to say volts, but you want to be always thinking of joules per coulomb every time you write that down or say it. So anything that I've got in a purple box here, you don't need to draw in your notes, just a little picture for us. If you go to the store and you see a battery and it says, hey, I'm a 1.5 volt battery, that's almost an energy value, right? It's almost like saying 1.5 joules, but it's just 1.5 joules for every coulomb that goes through that battery. If you're going to use a voltmeter, make sure you connect it up in parallel, kind of piggyback it onto the circuit. And you can just connect it up while it's running. You don't disconnect anything, and it'll tell you the voltage difference between two places in the circuit. So while this circuit is running and current is going clockwise, I can connect up my voltmeter before and after this resistor, and I could see how many volts we're actually using. We would say dropping as you go through that resistor. Or you could put a voltmeter around the battery and see how many volts you're gaining as you go through that battery. But just connect them up while it's running, just to 2 points before and after any device you want to look at the voltage for. Again, stuff in purple here you don't have to write down, it's just to see. This is kind of just some old school notation here. You'll see some people still hang on to this. Most people have gotten past this. But technically, If it's just a single cell in chemistry, right, that has the 2 electrodes, then we would draw that with a long line and a short line. If you want to put multiple cells together, that's when you have a battery. So a 9-volt battery is indeed that. It actually has 6 little cells on the inside, 6 little miniature versions of these. This is technically only a cell and not a battery, but you would be probably shunned if you said to your friends, hey, does anybody have any AA cells? We just call them all batteries. Now you'll pretty much only see this notation with lots of lines for the electric circuit if it's very high voltage, and you're supposed to be very careful with it. So we pretty much call everything a battery, but technically a battery is when you put multiple cells together. If you actually tear apart one of these 9-volt batteries, you'll see that it's not quite arranged this way physically, but electrically it is. There are actually 6 of those, and they're just connected together. That way, each of them being 1.5 volts gets you to that total of 9 volts for the battery. And that is, I'm pretty sure, that's the end for lesson number 1 for chapter 6.